first 2 days will be basic, very generic course. Then from third day, fourth day, fifth day will be more technical, which is very much related to the proton therapy course. And what else? So these are the things. Maybe few participants will join after some time. I think that's fine. Anything else that you, before we start, if you, at least those who have come from outside, anything that you have any concern or anything? Nothing so far? Okay, so then I think please go ahead with the introduction. Okay, so by now you might have already known, my name is Gian Giri and my colleague Saurabh Sandil. So we are the coordinators. Okay. You can go. Maybe start from here.
I am Adit Francis. I am a second year MSc Medical Physics student here.
My name is Chitra. I am from Sangat
Lecture, and first lecture it will be a story of I titled it the quest for fundamental. So fundamental, it means uh, um, we'll start with the philosophy why people wanted to know about the fundamentals. Okay, so it has been in our civilization, I mean, with different civilization also. So they always wanted to know the fundamental building blocks of matter. Okay, so suppose if we have anything in front of us, say this glass, so you can cut in pieces and finally you will find out these are made up of atoms, or maybe table. So if you cut it off, there will be cells, and then further it will be made up of some hydrocarbon like carbon and hydrogens, so a lot of several elements. So thing is that fundamental is key. So what does it mean by fundamental? It means it does not have any internal structure. Okay, so I think we already heard several times in several civilizations there were fundamental elements like earth, water, fire, etc., whether it is Indian civilization or Western. So the story of nuclear and particle physics, how it involved, is the quest of fundamental, knowing about what matter is made up of and how do they interact. Okay, so little bit fast forward to Dalton's atomic theory. So we figured out there are elements, and those elements are made up of several atoms, different elements made up of different types of atoms. And those atoms at the time of Dalton, around 1800, they were considered indivisible. It cannot be destroyed. Okay, so they arranged in a fashion, it's called a periodic table. But the question that we pose is atom, the story end there? Like, is the atom fundamental? Is it made up of something? So by now you all know that atom is not fundamental. And what is the first elementary particle you can think of coming out of atom? Okay, electron. So since we are going through the discovery, the story, timeline. So the first thing that said that atom could be divisible, or some elementary particle popped out from atom, was electron, and it was discovered by J.J. Thomson. And this is his famous cathode ray tube, in which electrons were produced by thermionic emission. So there was some metal plate, tungsten maybe, and it was heated, and then electron popped out, and then you put some potential difference, it accelerated, and then you do several experiments to measure some quantity, like Thomson measured the E by M ratio, and so he put electric field and magnetic field, and measuring the deflection, he figured out the E by M ratio. Okay, so this was the actual setup of Thomson. The pointer, yeah. Yeah, so so this is the schematic. Okay, so as I was saying, electron was emitted through the thermionic emission, and this is the plate where you heat it up and you put it in the electric field. It is accelerated towards this, and then you put electric field and magnetic field perpendicular to each other, and you try to cancel out the different field, and you measure the deflection in the glass. The end screen is graduated, and you measure the amount of deflection, and you measure how much electric field you are applying, how much magnetic field you are applying, and then you calculate the E by M ratio. So this is a question I pose, and you should write it down and think about it during lunch time, okay? And we will discuss it, how E by M ratio can be calculated from the Thomson's apparatus, okay? Okay, so hint is, I think there was a MSc in medical physics. I think student already have done this exercise, but still. Okay, so Thomson measured this E by M ratio by, the hint is by cancelling the deflection by applying appropriate amount of electric field and magnetic field. So that's a hint. So anyway, let's come back to the result. So what it was found, what do you expect if I try to calculate the E by M ratio of a proton and an electron, which one would be higher?
Electron, obviously.
Electron, right? Mass is, the charge is similar, although it's negative and positive, but the mass is very, very tiny, 1,700 times tiny, okay? The E by M ratio is found to be, large. E by M ratio is found to be very large for the electron because mass is tiny. So, later it came to know, later Millikan measured the charge of the electron and figured out, okay, there is something, some different particle, so it's which came out of the atom, okay. So now we know from the work of Thomson and Millikan the charge and masses of, because you know the E by M ratio, you know the charge, so charge and masses are known separately for this electron. So let's try to build up a model. So you have a neutral atom, okay, and you know that there are some negatively charged particle which are electron which is coming out. So you try to put together a simple model where you think of your entire positive charge is distributed in a sphere. I would call it maybe a watermelon kind of model. So you can, red flesh is the positive charge uniformly distributed, and whereas the seeds are the electrons. Okay, so when you heat it up, it comes out. Okay, so one good thing to remember is electron volt, definition of electron volt. So it is the 1 electron volt is the kinetic energy gained by electron when you put a potential difference of 1 volt. Okay, so can someone tell what is the value of 1 electron volt in joule? Okay, this value you already know. Okay. So you can keep this, you can write all those numbers. So now we have electrons we discovered. Okay, so moving fast forward to 1906, people were doing experiments with alpha particle. They were hitting alpha particle in several foils, mostly students of Rutherford. Okay, so this is the setup of Rutherford experiment. So this tube you can see here is mostly, you connect it to a vacuum tube. This is a schematic. So you connect this cavity to a vacuum tube. So you pull out all the air. Why you need to pull out air? You're doing an experiment with alpha particle. Why you need to pull out air? Yeah, okay. So, you know, the alpha particle range in air is about centimeters, right? So if you want it to hit the target here, which is the gold foil, you need to pull out the air. So, so this setup is in the vacuum, and this is the source of alpha particle. I think it was radium or americium 241. I do not remember exactly, but it has to be a monoenergetic. Okay, why alpha particle coming from nuclear decay is monoenergetic? Because it's a two-body decay. Okay, so it's a monoenergetic alpha particle, and you make a collimated. You try to make a collimated beam, and it hit a gold foil here, and how do you see it? How do you observe the alpha particles? Okay, so you put a microscope and you coat the surface of the microscope with a zinc sulfide screen. So whenever your alpha particle hits the zinc sulfide screen, it produces a scintillation photon. Okay, and you just see through the eye. Okay, and this entire setup is rotatable. Okay, so this microscope can rotate at different angles, and you can measure the angle of scattering at. So you perform the measurement, you count at one particular scattering angle, you keep on moving, and you count the alpha particles scattered. Fine, this part is clear, right? Okay. So coming back to the schematic, I think you guys already know that alpha particles are helium ion, so 4He2, and so this is the schematic of the same thing. So I do not have to describe again, but I just wanted to bring your attention towards observation. So a majority of alpha particles are scattered at small angle. What do you mean by small angle? It means they were just undeflected. Okay, majority were undeflected or deflected very slightly. Okay, and a small fraction, majority, okay, a small fraction is found to be scattered at very large angle, okay, about greater than 90 degree. So that amount is about a small fraction, and almost 1 in 15,000 alpha particle, it was backscattered. Okay, so that was more surprising for Rutherford. Actually, this experiment was done by his students. Okay, and Rutherford interpreted the result. Okay, so this was very surprising that something you hit and it bounced back to you. Okay, so why it is so surprising, we will see in a moment in a simulation. So let me just pull out this one. So if we think of a plum pudding model, and so you can see here the red part is mostly positively charged from the Thomson's model, and if you try to shoot the alpha particle, it is mostly passing, right? Not much. If I track, it's mostly undeflected. Okay, and if I try to pull out the Rutherfords, okay, and you shoot the alpha particle, and if you just observe this screen, okay, so a majority of them are undeflected. A small fraction would be deflected by a large angle, and if you wait for enough time, you will see a backscattered alpha particle. And actually, you can go to a, this is the atomic scale, and you can go to a nuclear scale, and you can put the traces. Just observe the trajectory. We'll come to it in a moment. So you can see how they are getting deflected coming to. So this is a very zoomed up picture of it. Okay. Okay, so just observe the trajectory for a while. Okay. So anyway, so coming back to our lecture. So what I wanted to convey that large scattering cannot be explained based on Thomson's model of atom. Why is it so? Because you know the force between alpha particle and the nuclei is Coulombic, right? And you know that it depends on the charge of the nuclei and the distance between that. Okay, so if you, for the backscattered, you want to, what you want to do, you want to maximize the thing, right? You want to have the entire charge as well as distance to be smaller to have the maximum impact. So if you imagine Thomson's model, which is uniformly, nucleus is the atom is entirely uniformly charged sphere. So you cannot reduce, if you try to reduce the distance, the charge will be, you will be feeling lesser and lesser charge, because it will pass through your atom and you will feel only the charge which is enclosed inside this radius, right? But if you try to go further, you feel the entire charge, but the distance becoming larger. You're getting my point? Okay, so this backscattered thing, the maximum deflection, it cannot be explained based on the Thomson's model. So, to have the backscattered thing explained, you need to imagine the entire charge of the nucleus is concentrated at one center. Okay. So as I mentioned it already, so you need to have the entire positive charge of the atom. It has to be contained in a very small sphere, and we call that small sphere as nucleus. And whenever the alpha particle closes by to the nucleus, it experiences a strong electromagnetic force, okay, because it is now passing very small distance and it is experiencing the entire charge of the nuclei. Okay, so since the force experienced by alpha particle is central, the trajectories are hyperbolic, right? You have already seen the trajectories of alpha particle in that simulation. So those trajectories are hyperbolic, okay? And this also you know from your classical mechanics. If the force is central, the trajectories will be hyperbolic. Okay, so this is the schematic. We'll discuss Rutherford scattering and we'll calculate the scattering formula into tutorial session. But few things you should remember. So this is your scatterer, your nuclei, which is Z times the charge on the electron or on one proton. So and this is the distance away from which the alpha particle is passing. So this you call impact parameter. Okay, and if you connect this line, the asymptote of the track, okay, and the angle which is formed between the asymptote of the two tracks, like incoming and outgoing, that angle is called theta, the scattering angle. Okay, so this part you should just understand what is scattering angle as well as what is impact parameter. Okay, so what happens to the scattering angle when you try to play with the impact parameter? So this is your impact parameter so now you know that if you try to reduce the impact parameter, then scattering angle will be smaller or larger? Larger. You can see that in the diagram, right? Because you're going closer and closer to the nucleus. Impact parameter is reducing. It means you are going closer and closer to the nuclei, right? You can see it here. So I've drawn here the 4 scenarios, 1, 2, 3, 4. The scenario number 1, in which the impact parameter is very small, okay, and it is the most scattered one, right? Scattering angle is very large. Okay, so this is the thing you saw that in the simulation. So most of the tracks are hyperbolic, and these are plotted as a function of impact parameter and different scattering angles. Okay, so in the tutorial we'll try to deduce this relation, that impact parameter is having this constant, which is z prime. Z is the charge on alpha particle, z prime is the charge on the nucleus, divided by some constant, divided by the kinetic energy of the alpha particle, mv square some factor, and cot of the scattering angle divided by 2, right? So we'll try to derive that in the tutorial. Okay, so let me just fast forward to the result, and I will just try to explain the result, interpret the result. But will just to mention that was the relation between the impact parameter with the scattering angle, and then we'll also derive, this is called the Rutherford scattering formula, and we'll derive this and we'll see it later. But let's come to the result part of it, okay, in the lecture. So these are the, so now you imagine this setup that I mentioned earlier, this setup, right? So what you are doing, so you are putting a source here, you are putting a gold foil, and you are moving your microscope at different angles, right? And you are counting it for some time. So that is the thing. you fix it at one scattering angle, theta 1, you count it for 10 minutes, you move to theta 2, count it for 10 minutes, so on. So these are in the first column that you see is the scattering angle. Okay, so 150 degree, 135 degree, and so on. And you want to take out any other parameters which is not coming from the scattering, say for example background or scattered through the cavity of the lead box where you're keeping the source. So you measure it without foil first. Okay, you don't put a foil and then you put a foil and then you subtract it off. So without foil you might observe some count. Okay, with foil you observe some count and you subtract it off. So this subtraction will give you the actual count of it, right? And suppose you are counting for 10-minute window, you take account of the decay also. Okay, because in 10 minutes I think the activity is falling down, so you take account of that factor as well, and then you ultimately come out to be the corrected counts, say 10 minutes. Is it clear or any confusion here? Right? So this last column is corrected by taking out of any background thing, corrected by the radioactivity also, radioactive decay also, right? And then you calculate this factor 1 upon sine to the power 4 scattering angle, and if you multiply it leads to a constant, right? So if you try to multiply or if you just try to plot the scattering angle and this number of counts, you see a nice dependence on the cosec to the power 4 theta by 2, right? So this one is first observation you can see, but if you try to multiply by 1 upon this, you will see a constant. Is this part clear? So this was the validation of the Rutherford scattering formula that you see here. Okay, so other thing from the Rutherford scattering formula is we can conclude is that number of scattered alpha particle was found to be proportional to 1 upon cosec to the power 4, or sorry, cosec to the power 4 theta by 2, or 1 upon sine to the power 4 theta by 2, right? So this was measured, this was found experimentally, as well as we will try to calculate it. The other thing you might notice, can you tell me, looking at this formula, how the scattering is related to the kinetic energy of the alpha particle? Just look at this formula and tell me. Huh? So how the number of scattered alpha particle is related to the kinetic energy of alpha particle? I cannot hear anyone. Just look at, huh?
Inversely proportional to the square of kinetic energy.
Okay, very nice. Inversely proportional to the square of kinetic energy. Anyone, all of you can see, right? There is a mv square term, half mv square. Half mv square is the kinetic energy, and there is a square term, right? So 1 upon kinetic energy square of the alpha particle. And I don't have to go back. This part is also clear that the number of alpha particle is proportional, scattered alpha particle is proportional to the z square, which is the foil's atomic number. Okay, other thing which does not come from the Rutherford scattering formula is the thickness. Okay, this was found to be found experimentally, and if we try to increase the thickness, number of scatterers increase, right? Number of atoms, number of nuclei increase. Okay, so number of scattered alpha particle is proportional to the thickness of the foil. Okay, that you observe here. Okay, moving on. So from the Rutherford experiment, we found that nuclei is a point charge, concentrated point where all the charge of the positive charge of the atom is accumulated, right? This was the conclusion from. But can we get an estimate of the nuclear radius from the Rutherford experiment? Can we say something about what is the size of the nuclear radius? Anyone? Huh? Femtometer, but how? From the Rutherford. Okay. So what you do is that you know the kinetic energy of the alpha particle. How do you know the kinetic energy of the alpha particle?
It is inversely proportional to.
Who is saying? Can raise your hand? Yeah.
It is inversely proportional to scatter of angle of alpha particle. So.
But without, if suppose I give you a radioisotope, and can you know the kinetic energy of the alpha particle? I told alpha particles are monoenergetic, right? Right. So how it is coming? Because it's a two-body decay. So just by knowing the parent nuclei, daughter nuclei, you can know the kinetic energy of the alpha particle, right? Just from the two-body decay physics, right? So you can go, you can know the kinetic energy of the alpha particle. It will be mostly a monoenergetic, right? So what was the question? So now you know the kinetic energy of alpha particle. You look at the backscattered one. Only the backscattered alpha particles, right? So what happens? Alpha particle is coming from this direction. Nuclei is here. The alpha particle will reach to some point where its kinetic energy will equal to the potential energy, right? Gain, and then it will go back, right? So you try to, just from the kinetic energy of the alpha particle, you equate it. Half mv square equal to the potential R min. R min is the distance closest it can go to the radius, okay? So this will not give you actually radius of the nucleus, but it will tell you how close I can reach. And from that, you can say that, okay, my nucleus is not there till now. You can put an, if I say it more technically, I can put an upper limit on the size of the nucleus, right? I can say that at least nucleus is not here, I came back, okay, alpha particle came back. So equating this, R mean, I rearrange this equation, equating this, I can calculate an upper limit on the size of the nucleus, right? And from this calculation, I can figure out it happens to be 27 femtometer, okay? But it's a very, I mean, you will come to know in a moment that 27 femtometer is a large number, but quite good. We reached up to femtometer. At least I can say that the nucleus is of the order of femtometer, as you said, right? So this was it. What is another way to measure from Rutherford-like experiment to find the size of the nuclei is that you keep on increasing the kinetic energy, right? You keep on increasing the kinetic energy, and at one point the Rutherford scattering formula breaks. So what we are doing is that there is an alpha particle that you are shooting to the lead, to the gold foil, and you put a detector fixed at some angle, say it is 60 degree, okay, and you keep on see the scattered alpha particle, take a count. So what we are doing this time in the x-axis is not the scattering angle, this is the kinetic energy of the alpha particle, right? And you see how, if the Rutherford scattering formula is valid, how this curve should look like. If you try to fit, which function you will fit?
Or minus 6.
Decay from 60 per minus 6.
Why?
It is decreasing like this, the plot is like this.
What I am plotting in the x-axis, what I am plotting? Kinetic energy of a particle. So how does it go? Number of scattered to the kinetic energy, how does it goes like? So 1 upon x square, right? So you will fit it by 1 upon x square. So you will, this dotted line is 1 upon x square, right? So you try to, and these are the dots are the experimental curve. So this is your theoretical curve that you said 1 upon x square. And at certain point, the Rutherford scattering formula breaks. Why it breaks? Because you guys are all in MSc, so you should be knowing how many forces are there. 4, right? So Rutherford scattering formula is based on only on electromagnetic force calculation. Till now we have not considered that strong interaction is there, right? So if you try to come very close to the nuclei, strong interaction will just start, okay? And it will show some deviation in the Rutherford formula. So after this point, Rutherford scattering formula won't be valid, it breaks, right? So at this point, you will say, okay, I touched the nuclei, right? So from there, you can calculate the nuclear radius, and we will try to calculate in our tutorial, okay? And we'll figure out the answer will come roughly about 10 femtometer or lesser than that, okay? So this was, so till now, what was our story title? Quest of fundamental. We are trying to figure out what are the fundamental things, what matter is made up of, right? So we figured out it was made up of atom. Atom was found to be not fundamental. It is made up of electron and nucleus. So is nucleus fundamental? No. Okay. So after this scattering, somebody was saying yes. Is nucleus is made up of something? Proton and neutron. Okay. So same Rutherford discovered proton. Earlier, I think proton was known. How it was known? People were doing this cathode ray experiment, right? There were also canal rays experiments where ions were. So can I call proton as hydrogen ion? Safely I can say, right? So you can figure out in canal rays, right? But it was more saying proton as a constituent of nuclei. It came from Rutherford. Okay, so these were already known, okay, and it is figured out that hydrogen ion had highest charge to mass ratio, and Rutherford revealed the presence of hydrogen nucleus or hydrogen ion or proton, and discovered as proton. So what he did, he bombarded alpha particle with nitrogen, okay, and figured out it gave off oxygen and proton. How Rutherford will how this setup would look like if I try to put nitrogen there? You just take out the vacuum, right? It will fill up with air, and air 70% is nitrogen, right? So if you just do that experiment in air, you will see this nuclear reaction. 14 nitrogen plus alpha gives oxygen plus proton. Okay, so in the ZNS scintillation screen, helium will have bigger spots, whereas proton will have smaller specks, kind of thing. And you can figure out it's not alpha particle, it's proton which is coming out. Okay, and this was, to be honest, I think I read in some article, this is the first nuclear reaction. Alpha plus nitrogen gave off oxygen plus proton. And what happened here? This is the first time someone changed an element from artificially. Okay, it was like a dream of alchemists, right? They wanted to make gold, so it cannot be done with any chemical reaction. Okay, if you want to make gold from other elements, you have to do nuclear transmutation. Okay, so this was the first nuclear reaction, and this particular reaction is honored in New Zealand's postal stamp. Okay, so is my nucleus contain which charge? Positive, and proton is positive, right? So we are done, right? We figured out fundamental elements or a fundamental particle, or is there any other fundamental particle in the nucleus? Huh? Subatomic. Which subatomic particle? Huh? Neutron and neutron and proton I just mentioned. So neutron just left, right? Okay, so how can you guess the presence of neutron? What happened is that so now we know that proton, okay, so nucleus has proton, and it has a mass of hydrogen ion, right? So if you try to increase, if you go to the second element, okay, 2H, which is helium, right? So its mass number should be 2 times the mass of proton, right? But we figured out it's 4 times the mass of the proton. Okay, okay, fine. I go to other element, lithium. It should be, if I somehow my formula works for 2 times, it should be 6 lithium 6, right? But it is 7 now. Beryllium 4 9. Okay, so something is weird going on here. Okay, so something there has to be something in addition to proton. Okay, you can guess the presence of neutron. So there was some historical thing which I will not go in great detail, limited time. So only thing I wanted to tell is so whenever the alpha particle hit these elements like beryllium, boron, and lithium, it produced a highly penetrating radiation, okay, which was not deflected in electric field and magnetic field. So most commonly you just say, okay, it's gamma, it has to be a photon or something like that. So that was the case. People were thinking that it was gamma radiation, but later the daughter of Madame Curie, Irene Curie, they discovered that this unknown radiation, whatever this neutral radiation, they kicked out proton from paraffin. Okay, and based on these things, later Chadwick did more experiment, and it was little bit unlikely that a gamma photon will eject a proton from paraffin. Okay, if you measure the kinetic energy of the proton, so they did the calculation and they figured out there has to be 50 MeV gamma ray to kick out a proton. Okay, why is it? And okay, let me just go to the next slide and I will explain it more. So what happened here is that why a neutron can kick out a proton from paraffin. Okay, so now we know that neutron and proton are of equal mass. Okay, so it is similar to your class 12 problem where you think of two equal masses, right? If you imagine balls of 2 equal masses, one ball is moving, okay, it hit the ball at rest. What happens to the ball at rest? It starts moving, and what happens to the ball which was moving? It comes at rest, right? So now what you are doing is that you are hitting neutron to paraffin. What paraffin is mostly made up of? Paraffin is wax, right? Hydrocarbon. So lots of hydrogens. Lots of hydrogen means lot of protons. So you hit the neutron, you hit the proton with a neutron, and a proton comes out. So this was actually happening there. Okay, so they analyzed the recoil energy of the proton and revealed that there has to be some other radiation which has a mass equal to mass of proton, and later on that's how the neutron was discovered. So there is a polonium source alpha particle which is hitting a beryllium target that give off neutron. Those produce neutron hitting a paraffin, lots of hydrocarbon, and that ultimately gave off proton, and that you keep on moving the GM counter, okay, such that you can figure out the range of the proton, and that's how you measure the kinetic energy of the proton emitted. Okay, so anyway, so I think James Chadwick got Nobel Prize for discovering neutron. Okay, so moving on, fast forward here. So after the discovery of, we started with atom, now we know nucleus, and we know that nucleus is made up of proton and neutron, and this is the picture it looked like. So earlier you had Thomson's model where you say that your entire positive charge is distributed like a watermelon and electrons like seed, and then after discovery of nucleus you say that your entire positive charge is concentrated as a point charge, okay, point size, entire positive charge, and all the electrons are orbiting. Okay, however, nucleus is not that big. Okay, although I just so not to scale, I mentioned not to scale. Okay, because what is the size of atom? Typically, angstrom, 10 power? Huh? Okay, and what is the size of nucleus? Femtometer. Okay, so 10 power 5 order difference. Okay, 5 order difference. And what happens? This nucleus, after discovery of neutron and proton, we figured out nucleus is made of neutron and protons. Okay, so are we stopping here? Actually, no. So most of the present day high energy physics experiment are the scattering experiment. So Rutherford experiment, I would say, is the mother of all the scattering experiment. High energy. What we do in high energy physics experiment, you collide two beams, you do a scattering, and you measure, you build up a detector in entire all the different angles. Okay, or you make the detector cylindrical, homogeneous. So this was just a beginning of the quest of fundamental. So let me just try to add one concept here. All of you know a de Broglie wavelength, right? Wave particle duality. I mean, because people are here from different background, so I'm just trying to repeat it here. So we know that all those so-called quantum particle or very small particles, they exhibit wave particle duality. They can be wave or particle, right? And suppose the particle, what we call so-called electron, a particle like, will have a de Broglie wavelength attached to it, which will be, the wavelength will be equal to h upon Planck constant divided by the momentum, right? This you all know, right? And if we think of a high energy electron, and if I try to write the energy of the total energy of the electron, what you will do? E square is equal to P square C square plus rest mass m square c to the power 4, right? And since it is high energy, okay, its momentum is very large, so its mass as compared to this momentum, I can neglect it, right? So I can say that E is equal to Pc, roughly, right? I can neglect in front of the Pc terms, okay? So I get the E is equal to Pc from there, and I can infer my momentum as P is equal to E upon C, right? All of you okay? Okay. So I can say that lambda, whatever my de Broglie wavelength, is equal to hc by E. Okay, just playing along with this equation. And hc is the constant, Planck constant multiplied by the speed of light. I am not in the SI unit, I am in some unit which is comfortable to me, where I measure the beam of electron in MeV and I measure the dimension of the nucleus in femtometer. So I try to choose this unit. Although this is Hc is 1.98 into 10 power minus 25 joule meter, I just played along with the units. Joule I converted to electron volt unit. That's why I told you to remember 1 eV is equal to 1.6. So from there you can get, and meter to femtometer is easy, right? 10 power minus 15. That's all. Nothing much. No fancy thing. Okay. So the question is that, can you calculate the de Broglie wavelength of electron beam energy of 190 MeV and 420 MeV respectively? Okay. So since the time is running out quickly, and so I will just tell you the answer. You can do this exercise later. Okay. So answer is, it's 6.53 femtometer for 190 MeV beam of electron and 2.95 femtometer for 420 MeV. Why I did this exercise, you will see it in a moment. Okay. So this is one concept, just to remember. Okay. Now, what you want to do is that, you all have done this scattering experiment in a single slit diffraction, right? So this one, one-dimensional slit. So, and then this is a circular aperture. So if you take a monoenergetic beam, that is laser, and there is a circular aperture, what do you see? A bright spot, and then a dark spot, and then a small faint bright spot, right? So if I try to plot this profile of intensity, okay, as a function of theta. So what you will see is that your intensity is maximum at 0, and then theta equal to 1.22 lambda by d, what you will see a minima, and then a maxima, it appears after. Then what happens? Second minima will happen at 2.23 lambda by d, right? If you try to do with a single slit, it normally happens at lambda by d, 2 lambda by d, 3 lambda by d, right? But it is for circular aperture. It is corrected for the circular aperture. Okay, just keep that in mind, that for circular aperture, first minima occurs at sin theta equal to 1.22 lambda by d. Just note it down. Okay, so from this, now can you connect both the things? Okay, these two are given. Now you connect both of this to figure out how we can figure out the size of the nucleus. Okay, what do you need for diffraction to happen prominently? You want the size of the aperture to be roughly of the same order as the size of the wavelength of the light that you're using, right? So that's exactly why. Now let me just connect the two concept I just mentioned. Is why I choose high energy electron beam. I wanted to probe nucleus as my scatterer. Now imagine nucleus as your scatterer, right? You want to go to that wavelength, your wavelength to be of that order. So that's why you choose these beams, okay, because you can probe that distance, okay? And your nucleus is an obstacle or your circular aperture, okay? So this is what exactly it was done. So it was not just a random number which I gave you. That's why I asked you to calculate 190 MeV, because there was a famous experiment done, electron beam scattering in SLAC. What they are doing is they were electron beam, and they deflected it, they put it under a slit, again they deflect. Why they are doing so much deflecting and bending is to reduce some sort of radiation. It's called Bremsstrahlung. Okay, if you just try to put it there along the beam line, there is a lot of Bremsstrahlung radiation. Okay, so you want to filter out all those Bremsstrahlung radiation. And ultimately you have a pure electron beam which is hitting a scattering chamber, and there is a spectrometer or there is a detector connected which you can rotate, right? Does this remind you of any other experiment? Just now we read Rutherford experiment, right? It is a scattering experiment only, right? You had alpha particle, a target, and a detector. Same thing is happening here also, right? There is an electron beam coming, there is a scatterer, and there is a detector which is moving, right? Nothing fancy. Only thing is that my energy scale, I just scaled up. Detector thing, I made it bigger detector. Okay, so this is how I zoomed it up. The picture is zoomed up and the schematic is here. You can see the, so mostly it is done with several gases like nitrogen and oxygen or something like that. So you want to make it as a gas chamber, and this is how you do experiment. And this is quite big, dimension is quite big. What do you expect if I try to plot as a function of scattering angle? What do you expect?
Sinusoidal.
Huh?
Sin theta is 1.22 lambda by d.
What you will see?
Sin theta is 1.22 lambda by d. So it must be sinusoidal also.
It must be sinusoidal. Okay. Okay. So you saw the intensity versus scattering angle, and first thing you should see is there has to be a minima at, as he said, 1.22 lambda by d, right? There has to be a minima. So you observed a minima here. Okay, you are doing a diffraction experiment, and So this was done with the oxygen nuclei with 420 MeV, and this was done with carbon nuclei 420 MeV. And you can see for oxygen nuclei, the first minima occurs at 40, roughly at 45, and again for carbon it's 50 degree. With these information given, can you figure out the size of the nuclei? Okay, the question is the answer is obviously yes, and I'll let you wonder till lunch. Okay, we'll come back in the tutorial session, and we'll calculate the size of the we'll calculate the nuclear radius from these two formulas. Okay, we'll review it again. Okay. Okay, let me fast forward my quest. Okay, the story was the quest of fundamental. We went to search for atoms, nucleus, neutron, proton, size of the nuclear radius. So now you're seeing that my experiment is becoming larger and larger. There's a need of high energy. Why there is a need of high energy? Because you want to probe smaller distances, smaller and smaller distances. So that's why we make bigger and bigger accelerator. Okay, and that's how electron, proton, neutrons are discovered. There's one more important thing for you guys, positron discovered. Okay, so positron we'll cover in a moment. Okay, and then neutron proton story does not stop here. People did experiment, people collided electron or I guess on proton. Okay, and they figure out the existence of quarks. Okay, in a similar way. I will not go in that detail. Okay, only thing is that there was some quarks discovered. So I just wanted to bring your attention to one important thing, which was neutrino. How many of you are familiar with neutrino? Only one, two. How many of you are not familiar with neutrino? Okay. So neutrino, we'll see. Yeah, so neutrino, what happens is that it mostly in no, I will not say day-to-day life or in day-to-day life. I think in bananas, right? There's potassium 40 which goes through beta decay, and neutrinos are emitted. Okay, and there are also you are getting lots of neutrino from atmospheres and all those things. But anyway, in context of nuclear physics, neutrino mostly you see in beta decay. Okay, what happens in beta decay? A nuclei transforms into another nuclei, and it gives off electron or positron. Okay, for simplicity, let's take this example for electron. So I started saying that for two-body decay, it has to be a monoenergetic, right? I will not do this calculation in 5 minutes, but trust me, okay, if you still have if you still have query about this equation, you can ask me in the tutorial. I can solve it. I can derive it. So if you try to calculate the energy, kinetic energy of the electron or positron emitted, you can easily calculate is mass of A square minus mass of B square plus mass of electron square divided by 2 into mass of A. Isn't it everything constant here? Is there anything variable here? If I have a nuclei, I know its mass, it's fixed. If it transmuted to another nuclei, MB, its mass is fixed, right? Electron mass is fixed. Everything is fixed. The electron which will come out will have kinetic energy fixed. Okay, in a two-body decay. That's how I was saying about alpha particle. It will be mostly fixed. So anyway, so if I try to now in my experiment, if I try to measure the electron energy, what you should observe? If your detector has a very nice resolution, ideal detector, okay, so you'll see a straight line or Dirac delta, or if you have detector resolution is there, a very tiny Gaussian here, okay, but ideally you will see a straight line, I mean a Dirac delta kind of thing. But that's not what we observed. We observed a distribution, okay, which starts from here and it goes towards the end. Okay, what does it tell you? It tell you that it's not a two-body decay. It's a multi-body. It can be more than one particle at least should be emitted. Okay, so let's not make situation complicated. At least one, it should be a three-body decay, and the third particle is we cannot detect it. Okay, I mean it's somehow it's escaping. So that particle is called neutrino. Okay, and okay, anyway. So neutrino was I will not go in great detail about just one thing. I will say that how neutrino was discovered. So there was compelling theoretical indirect evidence of neutrino, right? In the beta decay experiment just now you saw. You expected a Dirac delta like of curve and you saw a continuous distribution, right? So there was a compelling evidence of existence of neutrino, but there was no direct detection. So there was physicists, they tried to detect neutrino. Why it is so difficult to detect neutrino? Huh? Large path length. Okay. Ask this question, write it down, ask this question in the tutorial. Okay. Why neutrino is very difficult to detect? Huh? Lifetime is very large.
Weak interaction.
Okay, very nice. So it interacts only weekly. Okay, we'll come to his discussion. Okay. So anyway, so what happened is that there was one experiment designed. So there was a nuclear reactor which gives off lots of antineutrinos, electron antineutrinos. It hit a water target mixed with cadmium chloride. Okay, and let's not go into detail. Anyway, what is happening in antineutrino plus proton, it gives off neutron plus positron. It's like your beta plus decay. So if you put electron neutrino here, it will be a beta plus decay, right? Proton going to neutron plus positron plus neutrino. I just put this side. So what happens if your neutrino hit the proton? The water target means lot of protons, right? Hydrogen. So it gives off neutron and positron. Whenever a positron comes, it annihilates antimatter, right? It annihilates and gives 2 photons. Okay, and the both of photon will be 0.5 MeV each, and this neutron is absorbed by cadmium, right? In your nuclear reactor, you put cadmium rods to absorb neutron. Similarly here, cadmium absorbs a neutron and it gives, it goes in excited state and gives a delayed signal of a photon, which comes out after 10 that is a very nice signature, that you get 2 prompt photon and a delayed photon after 10 microseconds. So that is a very nice signature of measuring, identifying neutrino. So anyway, it was, and it is very nice. One story, it was told by one of my mentor. So what he was saying, it's called $1 million particle because the entire experiment setup costed $3 million. And after running for several years, I think I forgot to mention how many years, they detected only 3 neutrino events. So 3 neutrino at the cost of $3 million. That's why neutrino is called $1 million particle. Okay, anyway, coming to it, since the story started with the quest of fundamental, so we now figured out your proton and neutron, right? It is made up of quarks. Which quarks? Proton is made up of up, up, down, and neutron is made up of down, huh? Up, down, down. Okay. So first, okay, these 2 quarks. Then you discovered electron, and we discovered neutrino. That's it? It happens to be very weird thing happened. It happens to be nature on most of the times. Most of our universe is made up of this. Okay, I mean whatever things that you see, it happens to be nature give a second and third copy of this. Okay, so you can ask me about this later. Why? I mean, it was just discovered. It's not why. There are 3 generations, and there are force carriers, like strong force carriers are gluons, electromagnetic force carriers are photon, W and Z bosons for the weak interaction. But normal matter that we see is just a 5% in the entire universe. There are lots of 95% is dark energy, dark matter. We don't know anything about it. Okay, what it is made up of. So many unresolved questions. So this is one thing. And I said, let me skip this. I will come back later. So about antiparticles. So this is the thing I just showed about the particles. There are another antiparticle of it. There is U bar, up bar, and there is electron. Electron antiparticle is positron, mu minus mu plus. So there is particle copies of those things also. Okay. Anyway, so my time is up for this lecture. I will pause here. That's it. Yeah. If there is any question, you can go for a break, or I will go for a break. I don't know.
Said that it's a Gaussian function.
Huh?
In neutrino, you have said that it is like a Gaussian or direct delta curve.
Direct delta theoretically.
It is looking like a Heaviside unit step function curve. And I recently read a paper about particle physics. So even in Crane, they have updated that it's a Heaviside unit step function.
Which one? Neutrino?
Yes, yes. Theoretically.
No, not at all.
It's looking like that.
No.
That one.
No.
Okay.
Okay. We'll discuss it. Okay. Anything else? So let's take a quick break and we'll come back because again I have to speak for 1 more hour. Hello, sir. Hi, nice to see you again, sir. Again, there's one more. Narayan's house. It was Narayan's.
How can we bring this technology to the lab?
Huh?
How can we bring this technology to the lab?
Yeah, maybe they can answer. Which technology?
What are the therapy you're talking about?
Oh, no, I don't. Yeah, it was mostly new.
In R&D,
Yeah.
how can we bring it?
Yeah. That's a good question.
My curiosity is that only.
Okay. Yeah, I think Narayan Sahu will tell about.
Yes, it's important to address.
Sure.
Now, we talk about ethical things.
Yes.
Now, proton therapy is there in cancer labs. There are two instrumentation. In Apollo Chennai.
Correct.
There is one. Then they say that Faridabad also is one instrument
Yes. Might be.
for cancers.
Yeah.
So my curiosity is only to understand for cancers.
Yeah.
That's the reason I came from institute just to understand that.
Sure.
Dr. Bure?
Dr. Ure.
Yes.
Nice meeting
Anjan.
you.
Still recording? Stop now? Now you're not recording, na? Okay. You guys have already read. Yeah. My sound was okay, like last time. Okay. You work with Deepak sir? Oh, so so my story is over about the quest of fundamental, right? So now we know nucleus, and we'll be talking of some of the phenomena from the nucleus, which is radioactivity. And I think most of you are expert than me. Okay, earlier it was high energy physics. So I come from high energy physics background. So yeah, so tell me if something is wrong, I'm telling. Okay, so radioactivity, we know already that there is a spontaneous emission of some radiation. Radiation, either it could be charged like alpha, right? What is the charge on alpha? 2 plus, and then it could be beta. Like beta can be both. It could be either electron or positron. Okay, and there could be some electromagnetic radiations also, okay, like gamma, okay, and at very rare cases, nuclei also give off protons and neutrons, okay, very close to the drip line. We'll not talk about drip lines, but just to, okay. So what happens is, in a radioactive decay, there is so-called unstable nucleus, okay, that transforms into um, the stable one, and then it emits a radiation. So as I mentioned, it's mostly alpha, beta, and gamma. And there's one important thing you should understand, is that radioactivity is a probabilistic process, okay. What does it mean by that? Like, what I wanted to tell is, suppose I have a sample, or suppose I give you a nuclei, okay, and I tell you its half-life is, or give me a real cobalt-60. Do you know the half-life of cobalt-60? Okay, I trust you. 5 years, roughly 5 years. So I give you a nuclei of cobalt-60, one nuclei, and I tell you that its half-life is, what is the full life? It would be 0.693 multiplied by T half, right? So, so anyway, X years, okay? I wait for the average life of the cobalt-60. What will happen? What do you see? It will be gone? For sure? The answer is it may not, okay, because it's a statistical process. So it's statistical or probabilistic, okay. So what you need to do is that you have to look at a large sample of the nuclei which is unstable, okay. You take millions, billions of it in a sample, and then you observe it. So now coming to the half-life, after 5 years, if you see cobalt-60, suppose it is X amount, X atoms, it will become X by 2. Okay, X is a very large number. Okay. Yeah. So, rate of decay is very attached to how fast it will decay is property of a nuclei. Okay, how unstable it is. The measure of how we can figure out the measure of instability? How you can know the measure of instability? A nuclei is stable or unstable? Suppose I give you a nuclei, I tell you its mass.
Higher masses may be stable.
Higher masses to what? Okay, so binding energy. Okay, so binding energy per nucleon. From that you can tell the degree of instability attached to it. Okay, so anyway, so I don't have to. I try to put it more towards medical physics students, or to the context of this course. So anyway, so all of you are familiar with this symbol, right? Okay, there is a one, so just to mention about this logo, you should know about this logo. So there is something as the center, this dot, it represents a nuclei. Okay, and you have done in organic chemistry the wedge, right? Wedge coming out, something is coming out. If the wedge is opposite side, something is going that side, right? I think mostly in organic chemistry people use this. So something is coming out. There are three things, trifoil, okay, trifoil. So, or trefoil, whatever. So the three things which is coming out, which is alpha, beta, and gamma, that represents. That's how the logo of radioactive things is there. Okay, radioactivity, as it was accidental discovery, I would say, discovered by Henry Becquerel. So what he was doing, I think, before his time, I think Roentgen already discovered the X-rays. Okay, so how X-rays are produced? Exciting electron, and then it gives X-rays. Okay, there could be a characteristic, and there could be a continuous from the Brunstrom process or something like that. So what he was trying to find out, there were some phenomena called phosphorescence, and whether it is related to the X-ray or not. So he was trying to do, I don't know the exact story. So what he was trying to do, he takes some material of uranium, for example, or something. So he put it under X-ray, and take it out, it gives phosphorescence. Okay, and suppose you put it again in the sunlight. Okay, and that's how the phosphorescence material work, right? So similar thing he was planning to do with some sample. It happens to be uranium, I guess. I think it's not mentioned here. So what he did, he was planning to do irradiate with X-ray. He wanted to irradiate with under sunlight, and he wanted to connect whether X-rays are connected with phosphorescence or not. Okay, so that was his aim. What he did, at that time it was cloudy like this, and then he postponed his whatever his plan, and he wrapped it, the sample, he wrapped it in a black paper, and then in a drawer he kept the photographic film like this, and that's how even it was not irradiated neither with X-ray nor with sunlight, still you see something is coming out. That was very weird to him. Okay, and it happens to be it was placed on top of a cross. So, and it formed the image of the cross also. That is an actual thing. So anyway, so later it concluded that it is not independent of the exposure phosphorescence or something, and then this phenomena he called uranic rays. Till now, still people confused. I think I can understand why Becquerel was confused. Still, if you see something is showing phosphorescence, like you put in a phosphorescent sticker, oh, it's radium. You will say it's not radium, it's not radioactive, it's phosphorescence. Okay, so I can completely understand why Becquerel would be confused with this. Okay, now moving on. Later, Marie Curie, I think, did some pioneer work for radioactivity. So she wanted to investigate. At that time, it was called uranic rays because it was coming out from the uranium, and she took a lot of different isotopes from the uranium, and she figured out more the amount of the isotope is present, more intense the radiation which is coming out. Okay, and later she found a different element, isolated thorium, and she discovered several other elements also, I think polonium and radium also, and that's all. And it was I think she also made, I think her husband made this electrometer through which the radioactivity was discovered. So they both worked together on this radioactivity. Okay, anyway, so Madame Curie was the first person who coined this term radioactivity to describe this phenomenon of spontaneous emission of the radiation. Okay, moving on, as you were saying, it is mostly connected with binding energy per nuclei, or we can see, let's try to see if I try to plot the different nuclei in a graph. In the x-axis you put neutron number, in the y-axis you put proton number, and you see this kind of island. Okay, it's nice, in the nice island, and this is your straight line n equal to z, and up to 20 or up to even 20 to 30, I would say, or 20. So most of the nuclei are stable. The green line represents the stability thing, okay, and the yellow ones are unstable. Okay, so the green line, the stable isotope lies when the n is equal to z. Okay, as soon as you go heavier and higher and higher, so the Coulombic repulsion from the proton, okay, they try to, because I think, let's not pretend, now you know that strong interaction is short range and Coulomb interaction is long ranged. Okay, so if you try to put more and more proton, the Coulombic repulsion will be dominant. Okay, and to make the nuclei bound, you want to add more neutrons to compensate the to make the nucleus bound, and that's how it is bend. Okay, it is nuclei will be more stable for higher neutrons. Okay, and what do you see from this side? If you try to slice off, if I try to mentally draw a horizontal line in this side, so the right side of this one, okay, take my hand, right side of this one, what you will have, higher neutrons, or higher, this will have higher neutron, this side will have higher protons. Okay, so how to go back to this one? If you have higher neutrons, you go to do beta decay. Okay, beta minus decay, neutron converting to proton, and this side, if you have, you need to have beta plus. Neutron converting to proton, it will be beta minus. Yeah, and proton converting to neutron, it will be beta plus. Yeah. Okay, so the same thing I plotted. I got this plot from somewhere in the internet. So this side is again neutron versus proton line, and here I try to put which kind of decay the nuclei go through. So as I mentioned, if you try to draw a horizontal line, this side is neutron rich nuclei. Neutron will convert to proton, so it's a beta minus decay. So this side of the black curve that you see is all the nuclei exhibit beta minus decay, and this side all the nuclei exhibit beta plus decay. Okay, and if you go in a far end, okay, you see some black dots here, blue dots here, and here you see some orangish dot. So if you go here, if there are excess neutrons, nuclei can give off neutron itself, and there are excess protons, nuclei can give off proton also. What we call a neutron separation energy and proton separation energy is tend to be positive for that, and then it just give off proton and neutron. Okay, and if you go further higher, these type of nuclei, very heavy nuclei, they give off alpha particle and try to become stable. Okay, so this is alpha and beta decay. Let's try to, what I did in this plot is that I zoomed it up. I super zoomed it up. Okay, and what I did here is again the same thing, neutron versus proton number. So you can see neutron number, proton number. So I figure out where is the gold should be 79. Okay, I try to zoom the picture. Okay, so this graph is zoomed up image of that. So what happens if you try to draw a horizontal slice of it? Okay, those are all isotopes. Why? Because this side is Z number, proton number. Okay, proton number. What happens in isotopes is the proton number is constant and neutron numbers are varying, or the mass numbers are varying. So this is, you can see all the these side, all the in the horizontal, all are lead, all are thallium, mercury, and like that. These greens are the stable ones, the stability curve that you saw. Okay, and if you try to put a vertical line, these are isotones, right? So neutron number are constant and the proton number, the elements keep on changing, mass numbers are different. And if you try to put a diagonal line, okay, so that becomes isobar. It means mass number is constant and the neutron number and the proton numbers are changing. But very clear, right? Nothing, no fancy. So you should understand what is isobar, isotope, and isotones. So from this, again, I try to, and that's very simple, is the radioactive displacement law. So I think there are some scientists, they describe a law, but that's very simple to understand. Alpha decay, what happens in alpha decay if the parent, so again this is Z by N plot, Z versus N, and this is your parent nuclei. So what happens if that parent nuclei go through alpha decay? So what is alpha particle? 4 helium 2, right? Helium nuclei. So mass number changes by 4 and atomic number changes by 2. So you make that change. So this is Z versus N. So you can do proton number changes by 2, neutron number changes by 2. As simple as that. Okay, so your alpha, if the parent nuclei is here and goes to alpha decay, it comes here. Okay, now so you can write it down. In alpha decay, what happens? The Z reduces by 2, N reduces by 2. What happens in beta minus decay? In beta minus decay, proton is converted to neutron is converted to proton and an electron and neutrino. Okay, so so if the neutron is converted into proton, what happens? Your Z number changes by 1, right? Increases by 1. So so this side. Okay, so if beta minus, so this example is for alpha decay. The famous example is uranium 238 decay, which goes to thorium and alpha, and for beta minus decay, carbon 14 goes to nitrogen 14 plus electron plus neutrino. Okay, so your Z number also increased by 1 and the mass number. Thank you. Okay, so do you remember I gave example? I searched for the example very specifically. Where do we use this carbon 14? Carbon carbon dating, radiocarbon dating or something like that. Okay, now beta plus decay. Okay, so beta plus decay happens. So what happens in a beta minus decay? Write it down. Z number increases by 1 and N decreases by 1 and A remains unchanged. A is equal to Z plus N. Z increases by 1, N decreases by 1, A remains constant. For beta plus decay, what happens? Z decreases by 1. Earlier it was increasing because the proton is being converted to neutron. So Z is decreasing by 1. N is increasing by 1. A remains constant. That's how it becomes. So one example is this fluorine 18, F18 goes to oxygen 18 and it gives off positron and an electron. Where do you use this decay?
FDG production.
Say it. FDG, yes. So I think you use in this imaging, PET scanning, right? So medical physicists should help me, please. Okay, so you use this kind of thing in PET scanning. And okay, and other thing is that in beta plus, one other form is that what you can do. So in particle physics, you can always cross the reaction. You can bring from left side to right side by changing it to antiparticle. Okay, or right side to left side by changing it to antiparticle. So here is this positron. Okay, I change it here, is the same beta plus decay. So positron becomes electron, antiparticle, right? I'm moving it from the right side to the left side. Proton plus electron gives neutron plus neutrino. Fine. What happens here? Z number, N number. Same rule. Okay, nothing happens. Okay, same rule. So proton is reduced. Okay, proton is because and okay. So tell me which electron will be more likely to get absorbed? KSL, because it's very near to the nucleus. Okay. So anyway, and the example that I give here is this potassium 40. It absorbs K shell electron. It becomes argon. And where it is used? Tell me where it is used. Okay, it is mostly used in the rock sample datings. Okay, so we'll see how it is done. Okay, in an example. Let's move on. So as I mentioned, the lifetime of the radionuclei are statistical, unstable nuclei are statistical in nature. And if you observe a collection of some unstable nuclei, they don't decay at the same time. it's not like that you will see you will as I was mentioning is exactly become 1/2. There is some fluctuations, okay, within the uncertainties, okay. So they don't decay at the same time. So now we try to derive. So what happens, a nuclei P which disintegrates to a nuclei Q, P becomes a Q. And what happens, P decreases with time, number of P decreases with time, number of Q increases with time. Let's, for our calculation, let take N to be a very large number. N is the sample size, okay, the count of the nuclei P at T equal to 0. Okay, someone give me freshly prepared P nuclei, okay, or I start my timer at that time where T equal to 0 is when I start my stopwatch and count the number of P. Okay, so what we observed experimentally, this is experimentally observed, that the sample activity, what is sample activity, is exactly equal to the rate of change of the nuclei. How does the nuclei is transforming with a function of time, dn by dt, okay. The rate of change of nuclei is called the activity, sample activity, just keep in mind. So it is proportional to the number of nuclei present at that particular time. Okay, if I try to measure after time t, so your rate dn by dt will be proportional to n at that particular time. Okay, so rate will be increasing or decreasing, or will remain constant, right? Because dn by dt is going down with the time, okay, n is decreasing, okay. So dn by dt is proportional. So more nuclei you have in the beginning, it means more decay, more activity is there. And if you just let it wait for 10 years, the activity decreases, as simple as that. So dn by dt is proportional to n, or dn by dt is equal to lambda. I put a negative sign because it's decreasing, so the rate is decreasing, okay. Since it is proportional to n, I put a constant, okay. I call it lambda, and lambda is called disintegration constant. And the lambda n is called the activity, lambda is called disintegration constant. Keep that in mind, write it down somewhere. We'll calculate this formula. I think it's very easy to derive. I think you have done in class 12th, that nt at any time the sample is equal to n0 at time t equal to 0 multiplied by the exponent, the exponential coefficient is lambda times t. Lambda is a disintegration constant, as I mentioned. Okay, so I plotted it. Okay, this graph I plotted, and I put t half here just by hand equal to 5 hours. So you can, one thing you can nicely see is the p and q, right? So p is decreasing exponentially. You can see that, and q is increasing 1 minus exp of the p, right? It is also increasing. Okay, so this part again, but it's very easy to infer if you just write it down for now. If you do not see, we'll cover this in tutorial, that the probability that an individual nuclei, I think it is covered for most of you. So probability that an individual nuclei which is selected at random, okay, from the initial sample, which is at t equal to 0, you select at t equal to 0, you have lot of samples, you select some nuclei, and you figure out what is the probability of that nuclei will decay in time t and t plus dt in between. Okay, that happens to be exp minus lambda t times dt. Okay, if you don't see that, we'll derive. It's very easy to understand. Okay, so so that is your probability density, and you want to make an average, so you multiply by t and you try to integrate it from 0 to infinity. Okay, and that's how you get the average lifetime. And if you can solve this integral, okay, how do you solve this integral? Huh? integration by parts or something. Okay, we'll solve it during tutorial. Okay, just believe it. Just believe me for now that t will give you 1 upon lambda. Okay, okay. If I don't solve it, remind me. Okay. So this is the average lifetime. I call it average lifetime or mean lifetime. Okay, average lifetime or mean lifetime. So average lifetime or mean lifetime is equal to tau is equal to 1 upon lambda. Fine. The question that I pose is, what is the sample size after time elapsed t is equal to 1 upon lambda is or average lifetime? What happens to the sample? Is the entire sample vanishes because lifetime is over? I give you 1 million sample of it, of a nuclei, right? What happens to the nuclei after the average lifetime? Sorry?
You convert to another atom. Convert to another atom.
Convert to another nuclei. Entire sample. After
Copper 60. After 5.26 years, half of nucleus convert to nickel.
Okay. What I'm saying is, you wait till average lifetime, and what will happen? What is the sample size? That's the question. The entire sample will be gone. Huh? Size remains same. Number. Size means I'm not saying the number of nuclei, parent nuclei.
Parent atom or
Okay.
counting atoms.
Huh?
All atoms same, but it's only conversion atom.
All atoms remain same, only conversion happens. It means parent becomes daughter. So, okay. In your terms, in your terminology, how many parent converted to daughter? All the parent converted to their daughter?
That means 1.44 into half-life.
How you got this? Okay, that's what I'm asking. Okay, so okay, thanks. So the question is that what happens to the number of nuclei after elapsing an average lifetime? Okay, so let's try we have an equation. So why to worry too much? Let's put that thing on the equation and figure out how much. Okay, so we had this relation nt is equal to n0 exp minus lambda t. You put average lifetime, right? So n tau is equal to n0 minus lambda tau, and tau is what? 1 upon lambda. Exp is to the power minus 1, right? n0 by 1. So sample size reduces by 1 by e. Okay, when I say sample size, means the number of the parent. That's all. Nothing, no fancy thing. Okay. Okay. So what is E is 2.718. So it does not disappear completely. It becomes 1 by E of that. And that's how I try to, let's go back to my plot where I plotted. So you can see here, since this plot is for T half is equal to 5 hours. So average lifetime, after average lifetime, what happens? It becomes 100 by this much, 2 point is lesser than 50, right? You calculate 100 by 2.713, get this number. Tell me how much 100 by 2.713. Roughly, quickly. 37. See, so it, huh? Okay. So I'm okay with the line. Now, but this is very difficult. Our life as an experimentalist will be very difficult to find. If someone gives me average lifetime and I again go to the lab, I see sample size reduces by 1 by e. E is like never-ending fraction. Okay, it will be very difficult for me. So I try to make definition which is more life of experimentalist becomes easier. Okay, so I will say I will quote in a different way. I will quote at what time my sample size reduces to n by 2 because I can count my sample size very easily through activity. Okay, at what time my sample size is reduced? Okay, because now both will be easily measurable. You can measure time very easily now. Okay, so sample size reduced. So tell me at what time the sample size is reduced to t half, and it happens to be very easy. Again, plug into the formula. So nt half is equal to n0 exp minus lambda t half, right? T I replace with tau half, and what happens to the sample when it elapses t half is exactly n0 by 2. If I talk of a large sample, I'm not talking of two nuclei. Two nuclei, it might be both remain. Okay, I'm talking of very, very large sample. So in that case, after t half, n0 will reduce to n0 by 2. Okay, and you do some algebra and then you can figure out if the algebra is in front of you. T half is equal to tau times ln2. ln2 happens to be 0.693. Yeah. So 0.693 by tau. Let me go back to my plot. As I said, I plotted with this curve from the beginning. I plotted with t half is equal to 5 hours. So if the t half is equal to 5 hours, what is the average lifetime? Give me the number. Don't look at the plot. Give me the number. Question is, if the t half is 5 hours, what is the average? Oh, okay. So which line is average lifetime? This one, right? This one. So you can see at average lifetime this line, and it was reduced to 1 by e. And the t half is 5 hours, right? 5 hours line, it becomes exactly 50. I started with 100. I'm calculating the fraction, so 50%. Right? You can see this line is plotted for t half is equal to 5. Everyone is okay. Why you will all look puzzled? Everyone is okay, right? At t half, the sample size I plotted for 5 hours. 5 hours, you can see it reduced by. And what happens to the Q? What is the... Can you see one very nice thing? They cross. Okay, it means 50% of the nuclei now what you are saying. Okay, it transformed into the daughter nuclei, 50%. 1 minus. Simple, very simple. My life is complicated because what happens, a particular nuclei not always go to one particular decay. It can have a possible different paths. Okay, like P can go to beta decay and can also go to alpha sometime. Like if you go for a higher, there is a possibility that it goes to alpha decay and beta decay. One would be favorable, one would be less favorable. That's a different story. But path is available. Okay, so my nuclei 1 can go to nuclei 2 with disintegration constant lambda 1. Disintegration constant is the probability of transforming that particular nuclei, and it becomes to nuclei 3 with a lambda 2 disintegration constant, and the total if I try to just measure the decay probability of nuclei 1, whether decay happens or not, you can simply add the different paths, different probabilities. So lambda, the total probability of the disintegrating would be equal to lambda is equal to lambda 1 plus lambda 2. Simple. And if I try to measure, because I'm trying to measure the half-life looking at a daughter, right? So if I try to measure the total half-life, so it will be related to 1 upon tau is equal to 1 upon tau 1 plus 1 upon tau 2. How it came? It's very simple, because from lambda is related to 1 upon tau, right? So from there you can calculate. And what about t half? Because I don't know tau, I know t half. So how does the t half relation would work? Same, you put 0.693 by t half, 0.693 by tau, and 0.693 by. So it will be the same relation. Okay. Now, what happens is that we assumed in our thing that a nuclei 1 goes to nuclei 2 and nuclei 2 happens to be unstable, right? It happens to be stable in our previous. It was, but in nature you can find a chains of decay. Okay, nuclei 1 decay to nuclei 2 with lambda 1, nuclei 2 goes to nuclei 3 with lambda 2, same thing goes on n number of times. Okay, that's how the different decay chain works in the nature, right? So it happens to be, I will try to solve this. Not exactly, I will try to solve for 2 steps. This was a very famous problem and it was solved by, if I remember, his name was Bateman, Bateman. He solved his differential equations, okay, and figure out all the things. But I will try to solve in the tutorial for 1 step. When 1 is unstable, 2 is unstable, and 3 is stable. Okay, we will try to see things. Okay, so now coming back to this one, I think I'm not missing anything which I want to tell. Yeah, so you can just get a feel how to write these equations. So like, for example, you start with dn1, right? So it decays, right? It just decays. There is nothing which producing it. It's there in the beginning and it decays. So you will put, how does it decay? With a decay constant, the disintegration constant multiplied by the sample size, lambda 1 multiplied by n1. But if you go to n2, it decays with the probability lambda 2, right? So it minus lambda 2 n2, and it is also being produced through lambda 1. So you will add a positive sign lambda 1 n1. All of you are there, you saw there in the, when the Q was increasing, right? So your N2 will be increasing by this rate, lambda 1 N1, because this N1 is decreasing to N2, right? It's very simple. N1 is decreasing by this amount, so N2 will be increasing by this amount and will be decreasing by this decay thing. Same thing you can keep on writing for the decays, right? Chains. Okay, and ultimately you can go to the nth step. Fine. So let me fast forward to radioactive decay series. Okay, I have to really be fast now. So there are in nature there are 4 decay series found. Uranium series. So it happens to be, you can go. These series are a factor of 4n. Plus 1, 2, 3, okay, or 4n plus 0, 1, 2, 3. So there are 4 series, okay. So first one is, and each series is characterized by the mass number of the parent one, okay. And so first one is thorium, you can write it down, thorium series, which is 4n, and what is the mass number of thorium is 232, right. Then Neptunium series, which is 4n plus 1. So 237. So 236 is divisible by 4 plus 1. 237 thorium, Neptunium. And then uranium series, 4n plus 2, 238. Okay, 236, which is divisible by 4 plus 2, 238. Okay, actinium series, which is 4n plus 3. Okay. And this one is artificial radioactive series. Why we'll see in a moment. Okay. So let's go one by one in the series. So here what happens is that, why I draw this thing? You remember, now you go back to mentally imagine that alpha beta, how I put this one. This one. Right, displacement law. Okay, so you write it down in n by z again, and you start with thorium. Alpha decay, it brings you to here, and this is this radium to actinium is alpha. No, which decay? Beta minus. Okay, although it is written, but you can figure out, right? then it goes to alpha, beta minus, alpha, beta minus, alpha. And here you can see there are two ways appears. When you reach bismuth, either from the bismuth, it can directly go to alpha and become thallium, or it can go to beta and then alpha. Okay, from that you can easily come out. Is that clear?
Yes.
Okay, so ultimately in all the series they all try to become lead. Okay, lead. So here in thorium 232, it becomes since it is 4n series, so it terminates at lead 208. Okay. So what I was saying is that what is the half-life of this one is of the order of 14 billion years. Okay, half-life of thorium is 14 billion years. So as compared to thorium, neptunium, what is the half-life is million, of the order of million years, right? 10 power 3 years less. So that's why it is artificial series. It's not found in nature anymore. It decayed already. So all the elements here, you can see all the elements had to be you have to make that in lab, okay, to have this, to observe the series elements. So all the elements that you need to see for the neptunium, that's why it's called artificial series. Okay, now that's why I mentioned, so all the member nuclide have half-life comparable, lesser than the age of the universe. So that's why it doesn't occur in nature. Now uranium 238, similar thing, it goes through a chain of alpha and beta. I don't want to add too much time here, and it stable end product is 206 lead. It also ends at lead. This one, now coming to this one, uranium 235, it also goes through several alpha beta transformation, and it also ultimately it ends at lead 207. Okay, so these are the different series I just wanted to mention. Let me quickly end this part with applications of radioactivity. So one, radioactive dating, what you call it. One is called KAR, potassium argon dating. Okay, so what happens is that you can actually date, you can find out the age of a rock by looking at the ratios of potassium and argon. So how it happens is that, so whenever there is always a potassium 40 present. So whenever it after volcanic eruption, potassium 40 is there in the rock, and it transforms into beta minus beta plus decay and electron capture, whatever, it transforms into argon. But when the rock is formed, there is no argon in it. Why? Because argon is gas. There is no argon. When the rock is formed, there is no argon in it. Only potassium was there. Okay. So that is when from the volcanic eruption, when the rock is formed, there is no argon. My T equal to 0 starts there. Rock is formed. Okay. After billions of years, argon gas will start forming in the pockets of the rock. Okay. I take the rock sample, I figure out how much argon is there, and from that, and how much potassium is present, I take the potassium and argon ratio. From that, I can date, I can figure out what is the time has elapsed, how much argon has formed, and figure out what is the time when the rock was formed through the volcanic eruption. And I think we can do an exercise on that during the tutorial. Okay, so that is very effective method to figure out, and you can date it for billions of years old samples. Another very nice thing is that is for inorganic thing, for rocks and other things. Okay, but if you want to go back in history, okay, most of the things are not billions of years lifetime, right? So if you want to date something for which is 5,000 years back or something, or organic material, if there is a fossil found, dinosaur fossil found, or if very some wooden artifact found, very ancient one. How do you date it? How do you figure out? I mentioned about carbon-14. Okay, what happens in the upper atmosphere? Carbon-14 is constantly being formed through cosmic rays bombard the nitrogen. I think through cosmic rays bombard the nitrogen 14, and carbon-14 is continuously formed. And those carbon-14 are becoming carbon dioxide, and the entire thing is in equilibrium. Like there will be always carbon-12 and carbon-14. So there will be a constant ratio because there is constant bombardment. Right? So carbon-14 is constantly being formed, and the ratio is constant, the equilibrium ratio of the carbon-12 and 14. We are inhaling, okay, that particular equilibrium ratio, or the tree is taking it, whatever. And suddenly, I don't say you, I die, or the plant die, or something like that, okay? And if my fossil is found after 4,000 years or something, that particular thing, whatever time, your t equal to 0 starts when my carbon-14 and carbon-12 is in equilibrium. Okay, when someone finds my fossil after 5,000 years, that carbon-14 and carbon-12 equilibrium ratio is distorted, right? What will be more? Carbon-12 will be more, or carbon-14 will be more? Huh? Carbon-14 will be more. 12 will be more because 14 is decayed, right? 14 is constantly being decayed. So we'll try to measure that. So it's very, very interesting, right? You can all do. Okay, very important thing. You guys are more expert on this chapter than me. I'll go very fast. I will go through it. Correct me, medical physicists, if I'm saying anything wrong. So medical physics, in medical physics or in radioactivity, people use several units, and each time they are being modified or something. There's an organization called ICRU, International Commission of Radiation Units, and they always give the units. Okay, so first unit is activity. Okay, activity, you can write it down also. So the unit of activity is becquerel, because decay per time. Okay, this is the SI unit. Okay, 1 becquerel is 1 decay per second. Always remember, 1 becquerel is 1 decay per second. And becquerel has replaced the old non-SI unit, which is Curie, coming from Madame Curie. 1 Curie is 3.7 into 10 power 10 decay per second. Write it down, 3.7 into 10 power 10. Although it has replaced, but it is still in use, very popular. Okay, if you still see your isotopes that are being delivered to you, still you will see some microcurie, millicurie, or source. Okay, so it's not like although they are replaced, let's forget about it. Remember it. 1 Curie is equal to 3.7 into 10 power 10 decay per second, or becquerel. How this weird number is coming from? Okay, Madame Curie's element is she was studying mostly radium. So it is the activity of 1 gram of radium. As simple as that. If you take 1 gram of radium, the decay per second that will be observed is 3.7 into 10 power 10. Okay. So 1 Curie equal to how many becquerel?
2.73.
Huh?
2.2.
What? No. You are reading my slides. You are not listening to my question. I asked previous one. 1 Curie is how many becquerel? 3.7 into 10 power 10. Okay. 1 becquerel is how many Curie? Reverse it. Now your answer is correct. 2.7 into 10 power minus 11 Curie. Okay. And there is one more thing you should remember is specific activity. I'll take 15 minutes. So, okay. Specific activity is equal to activity divided by mass. Because if you keep on increasing, the activity is increasing, right? You want something which is specific activity, is activity divided by mass, which is equal to, you do the calculation, ultimately it will come out to be disintegration constant times Avogadro's number divided by the atomic mass of that particular thing. Okay. Whew. Okay, now coming to karma, okay, or karma, I don't know how to pronounce, okay. So it is kinetic energy release in matter, okay. This thing is valid for uncharged one, okay, like gamma or neutrons, okay. So whenever this uncharged radiations like neutrons or this one, they interact with matter, they deposit some amount of energy, right? So what is the karma is the sum of the kinetic energy of all the charged particles that are being produced. Okay, ionization happens through charged particle, right? So whatever charged particle produce, sum of the kinetic energy of all charged particles that are being produced by gamma or neutron is called karma. Kinetic energy released in matter, as simple as that, karma. Okay, and the SI unit of karma is gray. Write it down. SI unit of karma is gray. Okay, and 1 gray, I said kinetic energy transferred per unit of mass. So kinetic energy measured in joule. 1 joule SI unit. Okay, 1 gray is SI unit. 1 gray is equal to 1 joule per kg. As simple. So karma is measured in gray, and 1 gray is equal to 1 joule per kg. Okay, and it is not the absorbed dose. Okay, it is just a dose which is being produced through the ionization. It is not the exact same amount. So you will be seeing gray is used in several other things, absorbed dose also, but karma is just how much is the kinetic energy that is being produced. Okay, so most of the time what happens if you take an X-ray, there is between you and the X-ray, what is the medium? Air, right? Mostly we try to derive air karma because the material is air before you and X-ray. Okay, so we'll come to it in a moment. I want to mention one another thing is called exposure. Okay, exposure is again a measure of ionization that is produced by X-rays or other gamma rays in a specific mass of air, and it is the quantity is how much charge is being produced of one kind. So what happens when your ionization happens? You produce a ion pair, right? Electron and ion. Okay, so you count only one type of charge. If you sum them up, it will be 0. So you have to count only one type of charge. Either you count electron or either you count ion. So how many one type of charge is being produced per unit of kilogram? Okay, so SI unit of charge is coulomb, mass is kilogram, 1 coulomb per kilogram. Okay, and this is the SI unit. Historical unit which is still being used is Roentgen. Yeah. Okay, so 1 Roentgen, 1 R, how it is defined as the amount of charge that is produced, 1 ESU of charge being produced in 1 cc of air at STP. Because if you try to change the temperature, pressure of air, it will change. Okay. So if you try to convert in SI to this old unit, 1 Roentgen is equal to 2.58, write it down. That is one number which is normally people ask. 1 Roentgen R is equal to 2.58 into minus 4 coulomb per kg. Okay. So these are ionization radiation being produced. Okay. Now if we try to look at the absorbed dose, now you start entering into the body. Okay. So how much dose ionizing radiation is being absorbed by per unit mass of it was earlier it was being produced, now it is being absorbed. How much absorbed in the material? Unit remains the same because how much absorbed energy per unit mass. Okay, earlier it was emitted, now it is absorbed. So unit remains same. So don't get confused. Okay. So 1 gray is equal to 1 joule per kg, but this time it is absorbed radiation. Okay. As simple as that. Other non-popular source of radiation unit is rad, which is in ergs per gram. Okay. So people still use, I think in medical physics, rad unit. So 1 gray is 100 rad. Okay. Convert this, you will figure out 1 gray is equal to 100 rad. So absorbed dose is important because it quantifies the energy which is actually absorbed by the material or biological tissue, and that this particular unit will tell you how much is the damage done, because that is the energy that is being absorbed by the material body, whatever. Okay. Okay, now absorbed dose is all type of alpha. For example, if you take alpha, beta, proton, right, whatever things which is absorbed by your body, not all radiation produce equal amount of damage to your body. Okay, why? I think you will see in the other lecture, alpha particle gives in a short distance a lot of pairs, lot of ionization. Whereas if you compare it with electron, it can travel a larger distance and can give off smaller ionization. Like, so similar amount of energy which is absorbed by electron and alpha, alpha is more damageable, or proton is more damageable because it gives a very localized high dose, right? In a short distance, it gives a very high dose of thing. So that's why alpha is more dangerous. So you have to put a weight factor, how much is the ionization power in each type of radiation. So it happens to be ICRU decides the weight factor. Okay, so X-rays, gamma rays, beta particles, and muons have weight factor equal to 1. Protons and charged pions has a weight factor equal to 2. Alpha particles or fission fragments with the nuclei when it fragments into goes through fission. So the weight factor is 20. And neutron, it depends on the energy. There is a continuous, there is a curve of it. You figure out which energy of the neutron you are talking about. Depending on the energy, its weight factor depends. Okay, it varies from 10 to 20. So this part is clear. Is this part clear? Now, what I call is the effective dose, equivalent dose. Okay, equivalent dose is HT, H with subscript T, equal to some weight factor multiplied by the dose that you are getting in gray. So how this particular thing you are measuring, dt, how you are measuring in gray, joule per kg, how much energy of each type of radiation, and then you assign a weight factor to it. Okay, so this is your equivalent, and that particular, if you measure your absorbed dose in gray, then it gives you your this equivalent dose in sievert, SV. Okay, now you understand how this you might have done, you might have seen millisievert or something, your dosimeter says, right? Millisievert, you guys have heard, non-medical physicist people. Okay, okay, so that's not yet, we are reaching there. Oh, there is one more factor. Okay, so that's how if you measure in if you measure this in gray, then this HT will be sievert, and earlier the unit was REM, right? Roentgen equivalent man. Okay, it's also a very gender imbalanced unit, sorry. So radiation affect both men and women equally. So anyway, so Roentgen equivalent men, REM. But anyway, I think nowadays REM is very unlikely used. I think in US it is still used, and 1 sievert is a large quantity, very large quantity. 1 gray, I think lethal dose is 2 to 4 gray. Okay, I do not remember exactly, but 1 sievert is a very large quantity. So normally annual dose is 20 millisievert. So you can imagine 1 sievert would be how large. Okay. So till now we are there, equivalent dose, you understood. Now we have to measure effective dose. If your radiation hit your hand and if your radiation hit your heart or brain, it's not equal, right? You have to put organ factor, tissue factor also, how susceptible it is to develop a cancer. If I would say that effective dose is directly related to the cancer, the stochastic effect of the cancer to appear, okay, or the probability of cancer to appear, because there is a tissue weight is applied, and that tissue weight tells you how susceptible it is to the cancer or the ionization effect of the radiation. These doses are, so earlier you remember in the absorbed dose, you multiply it by the weight factor with the, how harmful is the radiation. Now you put another weight factor, is the tissue weight factor, okay? And that tissue weight factor decided by the ICRU, okay? And ICRU it keeps updating based on the research, is active area of research, and you can see there are changes there. So if this diagram effectively summarizes the absorbed dose, you factor two things: how harmful is the radiation, how susceptible, how organ is related to the cancer, and that tells you the effective dose. So how effective dose is measured is again measured in sievert, because I multiply by the constant. Is that everything clear? So as I said, the effective dose tells you the exact biological risk. It quantifies the risk, and it happens to be, if someone receives 1 sievert of dose, there is a chance of 5% increase in the amount of cancer as compared to the normal people. Okay, if you sample out an average human and if you sample out a human which have received 1 sievert of dose, in that particular population there will be 5% more risk of developing a cancer. That is a stochastic effect of the cancer, not deterministic. Okay, deterministic effect is like you see a very high dose of radiation and you start to see NVD, right? Nausea, vomiting, and diarrhea, or whatever. Yeah, that is a deterministic effect. Okay. So, anyway, let me summarize. I'm coming to my summary. So we started with radioactivity. Okay, this is a very nice chart, very nice summary. Radioactivity, SI unit is becquerel, right? SI unit is becquerel, or other unit is Curie. Okay, I didn't mention about Rutherford, but anyway. Then we can see, right? Sorry. And then exposure. Exposure is coulomb per kilogram, how much charge being produced, one type of charge per kilogram. Then how much radiation your body is absorbing, that is in joule per kg, that is in gray. Then you multiply by alpha, beta, gamma, which type of different type of radiation affects tissues differently, and that gives you in sievert. And then you calculate the effective dose. Again, you weight with the tissues, and that gives you again in sievert, but that's an effective dose. Okay. One quick exercise here is that we'll try to see a person received is exposed to equal amount of dose radiation. Okay, a person is exposed to equal amount of exposure, one in which the whole body is exposed to 1 milligray of gamma, and here only head is exposed, and we will try to see whether they are equal or not. Okay, very nice exercise. So 0.12 in so since entire body is exposed to that much, bone marrow, colon, lungs, stomach, skin, you do a tissue weight. Since it is gamma ray, so what will be the tissue weight factor? Sorry, radiation dose factor? 1. So that's why 1 is used here. if you change it to proton or something else, 2 will be used here, right? So you multiply by the tissue weight factor, ultimately it comes out to be 1 millisievert. Okay. But only if only head is exposed, then what happens? You put thyroid, you put brain, you put salivary gland, you put the weight factor of all those things, some amount of 10% of bone marrow also, okay, because you see only 10% of bone is there, not entire bone is there. So you put how much amount of bone is present in the head, 10%, and 15% of skin is there, some from some survey, okay, you put that thing, and it happens to be equal amount of dose in which entire body is exposed, you are getting 1 millisievert. In other, if the only head is exposed, you are getting 0.07. Okay, so whenever you are working in radiation environment, you try to cover as much with X-ray. They put lead apron or something like that. Okay, one famous dose is banana equivalent. It's not SI, it's the fun unit. Okay, so if you, fun fact, okay, really fun. Okay, don't, there is no banana equivalent dose. Okay, so fun fact is that if you eat a banana emits what? Yes, okay. So if you eat a banana, you receive about 0.1 microsievert of dose. Okay, and from radioactive potassium. Okay, so if you, I just try to do equivalent. Okay, so if you, depending on what are the things that you are doing, is that if you try to do a chest X-ray, it is equivalent to 0.02 millisievert. Okay, 0.02 millisievert in SI unit. And it is equivalent to the normal day-to-day life also. We are exposed to radiation like cosmic rays, a lot of other things. That is exposed to, if you live 3 days longer, it will be compensating by that much amount. And that is equivalent if you eat 200 bananas. Okay. CT chest is even more radiation, 5.1 millisievert, which is equivalent to 51,000 eating banana. And there are other methods which gives you higher dose. And okay, very nice. One last thing is the relative doses from different radiation sources that you receive. Is that whole body CT gives you 10 millisievert of the dose. Okay, and radiation worker is 20 millisievert, right? Or 100 millisievert in 5 years, right? That is more better dose. I think it can go to 30 millisievert in 1 year, but average out as per India is 100 millisievert in 5 years. Yeah. So in average US house through radon, you get around 7.5 millisievert in an year. From cosmic rays, if you live in higher elevation areas near Nepal or Dehradun, those kind of area, if you try to live in higher thing, you get 5 millisieverts, right? And at sea level, you get about very less, 2.5. Oh no, this one is in a different unit, sorry, 250 0.3 millisievert. So this one is 0.8 millisievert, sorry. And if you live near the nuclear power plant, is less than 0.01 millisievert. So nuclear power plants are very safely made with all those. That's why many medical physicists also work for their safety on nuclear power plants. I think that's it. So we have, thank you. Yeah. So I think you guys are all hungry. We'll discuss questions in the, yes.
Effective dose that you showed the ICRC the challenge.
Huh.
So why is it changing in year-wise? How 1977?
Based on the research paper, I would say, I think I'm not an expert in this field. So I'm not. So earlier, the people thought reproductive organs were more susceptible to cancers. But later, everyone knows the reason. I don't know the reason exactly, but I think, yeah, I'm not sure. For example, bone marrow. Okay, what happens? I can just give you, for example, bone marrow. What happens is constantly producing blood cells, right? So suppose if you do a DNA damage to the bone marrow.